Good morning, everybody, and welcome to our session from the Quantum Technology Training for Policymakers. Today, we are going to talk about how it is possible to integrate quantum technology and artificial intelligence, the two big and important key technologies that are innovating and developing today. We have two important speakers today, and they are presenting two different sides of the community, more on quantum technologies and more on artificial intelligence. And we are very happy to present our first speaker, Sabrina Maniscalco. Please welcome Sabrina on stage. And Sabrina is the CEO and the co-founder of Algorithmiq Ltd, which is a startup focused on quantum algorithms and software. She's also a professor of quantum information and logic at the University of Helsinki and an adjunct professor at Aalto University in Finland. She serves as a vice director of Finnish Center of Excellence for Quantum Technology and is a member of the scientific advisory board of several international institutions. Sabrina is currently focused primarily on her work in Algorithmiq, and she leads the team with an ambitious mission of redefining healthcare and life science by integrating quantum computing, complex network theory, and artificial intelligence. We are very happy to have Sabrina today with us, and please welcome. The stage is yours.
Thank you very much. It's great to be here. I will start immediately by sharing my presentation. And I think you probably should be seeing it now. Just let me know in case it doesn't show properly, but it should be. So what I thought to do today is to give a perspective of what we are doing at Algorithmiq in integrating quantum and AI in the framework of healthcare and life sciences. And of course, if you think in a general terms, we know that one of the reasons why the whole quantum computing ecosystem has been flourishing is because we know that classical computers are hitting scalability and efficiency walls. In particular, if we have to tackle growing global challenges, we will need a new technology that combines AI and quantum. Some of the limitation of machine learning and AI could be complemented by quantum computers. For example, it is known that machine learning or AI really very often lacks understanding of the physical worlds, the laws of the physical worlds, while quantum can really simulate ab initio interactions of atoms and molecules. Also, of course, machine learning depends on training data sets, while in the case of quantum, you could think of generating synthetic data that are then fed into machine learning, so to expand the solution space. And of course, there are the limitations in simulating complexity, which in general rely on since the very beginning, on the whole, let's say, promise of disruptiveness of quantum computers. So what we want to do is that in the future, we want to apply this combined framework to healthcare and life sciences in order to provide faster, cheaper in silico simulations. And the way in which we do this is, as many other, not only us, is by really not thinking of a quantum computer as a replacement of a classical computer or a machine learning, but integrating these paradigms. And in particular, what we have developed and what we work on is an interface between quantum computers and high-performance computers and supercomputers, which is based on measurements. So for us, measurements and readout of the quantum computer is key, and we use it in order to scale up the use cases. In particular, I will talk about how we can use these both in terms of what we call the digital quantum interface, that includes many pieces and packages that have to work together in order to allow the application software, in our case it's called Aurora, to really develop real-world impact use cases in chemistry, life sciences, and in general materials. So I will want to focus specifically on one example, because I think it's the one in which we are more advanced in integrating quantum and AI. It's not the only way of integrating quantum and AI. But just to explain the idea, the example is photodynamic therapy for cancer treatment. So here we are talking about an alternative therapy to cancer. And this example is part of a program that was funded by the Wellcome Leap, the Quantum for Bio program. We are now entering phase 3. And it's important to notice how the structure of this program worked, because initially we spent basically 1 year to try to understand which are the best algorithms in order to provide quantum advantage, and then, in order to provide a combination of quantum and classical for tackling this use case. And then we did simulation in HPC. And eventually now we're starting the implementation on hardware, importantly combining hybrid, so using hybrid algorithms, so using machine learning and using quantum. The importance of photodynamic therapy relies in the fact that it's an alternative therapy to cancer, which does not have the terrible side effects that exist nowadays, for example, for chemotherapy, radiotherapy, and so on. And the reason why it is much lighter in terms of effects is because the patients generally ingest a drug, it's called a photosensitizer, which is not active. So it is absorbed by the cells, but it is only activated on the spot of the cancer by light irradiation. And this allows them, through this activation, to produce reactive oxygen species that kill the cells. So it's only in the location of the cancer that the cells are activated. That the drug is activated and kills the cancer cell. And it obviously reduces toxicity and is particularly interesting. However, importantly, we partnered to develop these use cases with IBM and Finland. Why this is important? Because this is an example in which the end user, in this case, the medical doctors of Cleveland Clinic, came to us with a problem. And the problem is that this pipeline, this drug discovery pipeline, lacks, so it's really until now done in the lab. So it would be much beneficial to do, especially the first part of the drug discovery, computationally. But however, classical computational resources are unable to do this. And that's why, in particular, considering that the interaction of molecules with light is a very quantum mechanical process, we thought this is an ideal example on how and why quantum computers could help. So end user need comes before, and then there is a study to understand actually, can quantum computers be better and how? So this is important. So in fact, we understood that there was reason to be hopeful for this, and we identified in particular, first of all, the molecule that we wanted to study. And this molecule, you see it here in the plot, is a molecule that is already in phase 2 clinical trials. So it's not a simple molecule. It's an interesting compound, and it has all the characteristics to be tackled somehow together using hybrid methods, quantum and classical. What is important here is that the type of processes that you want to simulate, what you want to do eventually is to optimize this molecule, the properties of this molecule, in order to target different types of cancers. Because, for example, skin cancer and stomach cancer or bladder cancer, they are different. For example, the light that needs to penetrate more in depth for stomach and bladder cancer, and less in the case of skin cancer. And how do you change the properties of these molecules? You do this by adding or modifying the tail that appear here in this molecule. And this changes in general, the electronic structure level. And the important point is that this the whole simulation of these properties is hard to do on classical computers. This is I will not go into the detail, but it's a problem that is really exponential when tackled with the best chemical methods. So we developed a very complex pipeline. It's a pipeline which is, you see here, 6 steps, and on top of that, there is a quantum computer. Initially, you have this pre-processing, then you have the calculations is run on a quantum computer, and then there is a complex series of algorithms that in post-processing allow to extract the energy of and the properties actually in itself. Now, where does the quantum computer, so the machine learning comes? So eventually, what we want to do, what we are doing, what we started to do as part of this program, is the creation of a pipeline which is integrated. So it's not just in the lab, but it is also computation. So if you see in this plot here, where there is written standard DD pipeline, you see the standard drug discovery pipeline, which includes target selection, hit discovery and hit to lead optimization, and other properties that will continue to be done as before. At the moment, everything is done in the lab, and this includes a lot of trial and error, and this creates really high costs and also high, let's say, timings for bringing a drug to market. Instead, what we want to do is to do hit discovery and to lead on the quantum computer, together with the pre-processing and post-processing, and then using this quantum plus AI for the lead optimization. So in this case, the way in which it works is that the quantum simulation will be used to evaluate properties for the drug, and these properties, of course, optimizing them to the type of cancer, and this will be in turn exploited in order to create potentials that assess the photochemical activation pathways. The most important part is that these simulations will then be used to train machine learning and to create let's say, a number of alternatives, leads that then can be optimized. So obviously, this means that in general, we cannot, so it is too complex to optimize, so to create ab initio simulations for all the possible alternatives that we have in the molecular compounds, but we use only few of them, and then we use them to train the machine learning and create ab initio molecular dynamics based on this technology. So this is in practice the plan. In conclusion, I know that I'm close to the end of my presentation, but in conclusion, we have developed the whole software hybrid pipeline, including the simulation quantum computer that are fed into the machine learning. And in the phase 3 of Welcome Leap, we will have demonstration on hardware. Of course, this is the first demonstration will be for 40 qubits, then 76 qubits and 100 qubits. Perhaps I forgot to mention that this number of qubits are only indicating the so-called active space of the molecule. So that part of the molecule is really hard to simulate because the rest can be simulated classically. So one part of the pipeline is understanding what is this active space. The larger is the active space, the more precise is the simulation of the properties of this molecule. And so in particular, we want to go until the limits of 100 qubits where classical techniques really fail. And the classical technique that is used in this case, because it's called DNRG, classical chemistry, computational perspective. And so we aim at doing, let's say, hybrid, what we call quantum boosted DNRG, that will outperform what DNRG can do. So combining tensor networks and quantum. And so eventually we already have, this is very recent, the first experiment on hardware with 40 qubits. So it's more than 3,000 gates. It's a very complex already now simulations, the first step. So we are ahead of our timeline. And we show that if you look at the error of the properties that we want to calculate, this error actually decreases. Our target is to reach 10 to minus 3, which is a very small error for chemical accuracy, and we are not yet there, but this is the very first round, so we are pretty sure that we will obtain it. But most importantly, we are already outperforming the DNRG calculations without the quantum computer with the same, let's say, resources, one dimension in particular. So it's particularly exciting, and this is eventually my main message that already now state-of-the-art quantum hardware and advanced quantum software can tackle relevant use cases in drug design and discovery, and we believe that we will reach the point in which this will be really so complex to be commercially and industrially useful in the next year or so. This is all, and thanks for listening, and I hope that there was no disturbance in my background. Thank you.
Thank you very much, Sabrina, for being that explicit and super sharp on time. And we hope it will find work with your flight. And we have one question in the chat from Daniel Marquis. and he's thanking you very much for the exciting talk. And just to understand better, is the slide where the diagram flow after phase 3 side, in which boxes are either quantum or AI used? So in the
You,
slide.
this one here, I think. Yes. So what we are doing within part of the Q4Bio is the quantum simulation. And we have, however, developed as part of our pipeline this. It's here, exactly. The second part, so we do have implemented, but not for this molecule. So we tested the training of machine learning, the usage of quantum simulation to train machine learning is something that we have implemented. We have not yet used it for this molecule, but we have used it for body type. That is a smaller and simpler molecule that is used as a benchmark really in photodynamic therapy. So it's we don't have it yet for this molecule, and the reason is very practical. This molecule is brought in phase 2 clinical trial by biotech Seralas, and we have now just reached out to them in order to get the data. So we will be doing it, and we will be using the data from this biotech, but we haven't started it yet. We have instead benchmarked it and finalized it using a simpler molecule called body type. Hope this answers the question.
And before we let you run quickly to the flight, maybe the last question I would like to ask about the timing that quantum powered processing is taking. Is there a difference between the timing? Is it faster? Is it longer? Or is it the same?
Yes. So what we know is that if you, in a way, we are doing two different things here. One is really the simulation of the molecule in a quantum computer, and the other one is the training. So with the simulation of the molecule, with the method that we have, sorry, I think it is here. I explained it here. So this method that we have, the whole pipeline, it's a method is here, that it is at worst gives the same results of the best classical method we are doing. So in terms of resources and also of timing, it really is strictly, strictly better. So it has strictly better performance than the classical method by construction, by definition. Then what we do with the machine learning is instead we are expanding the solution space of molecules by using data, synthetic quantum generated data, which are not available from Teralas yet because we simulate ab initio. Okay, so it's a way of expanding the space of the possible molecules in order to find the ones that optimize the property, depending on the different types of cancer and depending on the different types of mechanisms that you want to that should dominate. So it's a bit more it's more complex than just time. It's going beyond what you can do. But when it comes to the quantum boosted energy, it is even time-wise strictly better because we just can do only better by definition than energy. And unfortunately, I have to leave right now.
Yes.
But I hope that this was useful. And please do write me if there are more questions. I'm happy to explain more. And also my researchers certainly can explain even more in depth what about this. Thank you very
Great.
much.
Thank you very much, Sabrina, and good luck with your flight.
Thank you. Thank you. Bye-bye.
Bye.
Okay. Now we will move to the next speaker of our session, and I welcome on stage Philipp.
Hello.
Hi, Philipp. Philipp Slusallek is a scientific director and a member of executive board at the German Research Center for Artificial Intelligence, DFKI, where he leads the research area on agents and simulated reality since 2019. And he has been a co-founder of director and the director of strategy of the European AI initiative CAIRNE, which is, if I understand correctly, Kern is the second name of this initiative. At the Saarland University, he has the chair of computer graphics since 1999, and he was a principal investigator at the German Excellence Cluster Multimodal Computing and Interaction from 2017 to 2019, and the co-founder and director of research at the Intel Virtual Computing Institute from 2009 to 2017. And prior to join Saarland University, he was also visiting assistant professor at the Stanford University. Originally, Professor Philipp Slusallek studied physics in Frankfurt and got his PhD in computer science in Erlangen University. And he is now researching in a large span of interest dimensions on artificial intelligence in the broad sense, and simulated and digital reality, and real-time realistic graphics, and many other directions. We are very grateful to Philipp being with us today, and welcome your talk.
Yes, hello everyone. I hope you can hear me and see my slides well. It's my pleasure to be here today and to give you a quick, very quick view on what we're doing in this area of combining quantum computing and AI, two areas that are very exciting. And in this area, we jointly with the quantum computing people and the AI people, we recently published a white paper on how to combine these two techniques. What are the key challenges? The one approach here is to do quantum computing for AI, so going in the one direction, but there's also interesting applications of using AI for quantum computing. And so I can't go through all of the things we wrote and summarized in that white paper. What I will do today is just give you a glimpse into some of the techniques that particularly we are using to make it a little bit concrete. But let's quickly dive into that. By the way, this is joint work with two of my research, Antonio Macaluso and Matthias Klusch, who drive that research at DFKI specifically. So why quantum for AI? So I'll focus on that part. So first of all, quantum computing can really boost artificial intelligence by speeding, or on the one hand, speeding up the training, reducing energy consumption and other resources, and also solving some of the problems that are hard to solve with classical approaches. And that's by combining this can help us to actually have more efficient AI systems that hopefully eventually will benefit society, but also industry. And I think it's particularly interesting because Europe is really good on the quantum side and the AI side. So combining these two benefits in a really dual deep tech context is something I think is really interesting, in addition to the fact that I think quantum computing is actually a good fit for AI for various technical reasons that I don't have time to go into, but maybe we can address this in the question and answer at the end. Also, it is beyond the hype, right? I mean, we actually can show that quantum computing and combining this with AI gives us really benefits already right now. And so that's really an important step. And on the right, you see a little bit the development in terms of compute for AI models. So being able to address this maybe with quantum computing to some degree at least is a really interesting approach. What we're mostly doing here is hybrid quantum classic algorithm, which means somewhat similar to what you've heard before, is that we're actually looping in quantum computing with AI computing. So it's not, in our case, it's not a one-time, you prepare something, then you do some quantum computation, and then you prepare the results. We are actually looping this. So we're doing some preparation, as you can see on the right, then we're actually doing the quantum computing that you see in the kind of pink color here on the right. And then we read the results, and we might actually go through that loop multiple times. And this is really nice, in particular in this NISQ area where, right, we have fairly high error rates still, and it's not full quantum computing is not really practical at this point. But the combination of these two techniques that can help us reduce training costs, deal with hopefully larger model sizes, and also address some of the hard optimization problems. So let me quickly go. So what is quantum AI? It's really the use of quantum technology for AI applications, as I said, solving some of the hard problems. And we'll go through some examples here in the following. With the idea of, right, you would have a high-performance computing center where you do have a quantum computing that can work in tandem with the AI applications. So in the following, we've addressed a couple of application areas: computer vision, planning, multi-agent system, reinforcement learning. It's really important to keep in mind that AI is not just transformer large language models today, right? There's still a large range of application where we actually use different approaches and we combine them. And then we have actually two types of quantum hardware, and we're developing algorithms. Sometimes even that can be executed on both, sometimes only on one of them. Both are interesting for various reasons. So the first use case, I quickly don't want to go into details here, but here it's actually, as you see on the right, it's actually a project we did together with the car industry, which is about navigation. So how to control an autonomous car and we do that with a reinforcement learning. So essentially we let the AI system in a virtual environment drive the car, and then we criticize it. And that is the critical part. So the decision of how to drive the car is a classical neural network. You see this here, the actor on the slide here, that part. And we have a critic, which essentially looks at the output and then improves, hopefully, the actions. And that critic we actually execute on a quantum computer. And because the quantum computer can explore multiple states or a larger number of states, we can actually achieve a better convergence rate. So we can provide the right input for training the actor. We can reduce variance and improve stability of the algorithms, and overall really increase the efficiency of doing this. It's really the combination here that's critical of the classical hardware that then eventually will hopefully go into the car, right? So we don't have to have a quantum computer, but for training it, we use the quantum computer that's in the lab in an HPC environment. Another application is coalition forming. That's really important for a number of applications. You can think of that, for instance, in the energy area, where you want to dynamically combine a set of energy producers, right, electricity producers to users, and you want to minimize the transport of energy over the network to minimize the load there. So you want to combine them in the optimal way. Another application is actually for satellite communication, something like Starlinks and similar approaches. We actually use data from Starlink here, because the satellites have to communicate among themselves. So you want to optimize who they communicate with in order to get the best bandwidth and latency. And so here we developed the GCSQ algorithm, where essentially we put all of the satellites, to take that as an example, into one big group. We iteratively split the group in an optimal way into smaller groups, and we use that, a quantum annealer, to do that splitting in parallel. And then we iterate to do more splits if necessary. And that iteration, again, is happening on the classical side. And we can scale this to fairly large satellite networks already now. We significantly reduce link overhead and adapt to dynamic and constrained topologies. And you see this here, if you look at the graph on the left. The classical algorithm is in red here over the number of satellites. You see that for roughly 75 satellites, the runtime completely explodes, while the GCSQ, the quantum algorithm in blue here, this is on a remote computer. So this even includes the communication with a remote computer. And in green, you hardly see this because it's essentially the x-axis. That is if the quantum computer is actually local. So we can get rid of all the communication. And essentially we could scale dramatically further here. And so this is really, again, something that dramatically improves things. We can reduce, for the satellite case, we can reduce the communication by 30%, and we can speed up performance by a factor of 10 and more, depending on the number of satellites. So some real value here. And we collaborated with E.ON on the energy side, and we used the public Starlink data to really have a concrete, practical use case to demonstrate our algorithms here. And again, they depend on that combination of quantum and classical computing. And finally, for the third use case, I want to really have an unsupervised image segmentation algorithm. Right? In many cases in AI, we use supervised, so where someone labels the data and then we train from that label data. In some cases, that would be too costly. And so you want to do unsupervised learning. And here we, again, do that in a quantum setting using a graph cut optimization algorithm. So essentially, we can map the pixels onto the quantum computer and then essentially split the image into pixels that are foreground or background, depending on what exactly you want to be doing. And again, it shows that the combination of quantum and classical algorithms give us significantly better quality in terms of the masks that we're computing. We're outperforming the classical algorithms, which is really important. And you see here that the quality, the approximation ratio, were slightly worse than the classical algorithms, but it doesn't really matter much, right? So it's really the combination of both of those techniques. So to summarize, there's key findings. Quantum computing, even with today's machines, is already practical for a number of targeted use cases, and we have many more that I don't have time to go into here. It's this hybrid approach of combining quantum and classical AI, and it's really that Europe is in a leading position in each of the areas, and then in particular in the combination of those. So we really need to support and drive this further. Of course, there's a lot of still open questions. There's a number of limitations that we could, right, with better hardware, we could do certainly much more. There's a lot more to get in terms of how to combine classical and quantum computer to get even better algorithms for other use cases. And of course, I think we need much more experts in the field to understand both quantum and AI. There aren't many people who can do both of that, but it's really what you need to drive this area forward and reap the benefits for the European society and industry, of course. With that, there's many publications. In particular, I'm not sure whether the slides will be made available. There's this white paper that I mentioned in the beginning. There's a link here. You can also easily search for that AI and quantum computing white paper. Google should find that quickly if you don't have the link, where we discuss things in a lot more detail. And with that, thank you very much, and I'm open for questions if there are. I see there's already a question. Thank you very much.
Thank you very much, Philipp, for your presentation and use cases that you showed. And indeed, we already have a couple of questions in the question and answer sets that I'm going to read. The first question is from Anuj Mehrotra. And he's saying that the IBM recently introduced generative computing as a more effective framework for interacting with large language models, LLMs. Do you foresee this approach enabling more effective utilization of existing capabilities in noisy intermediate scale quantum, NISQ? systems on current quantum computing platforms?
Yeah, we haven't done work or research in that area yet. That's something that is on our agenda. But I would be absolutely surprised if that would not be true, right? It's one of the key areas that we in DFKI, the German Research Center for AI, focus on is really AI understanding the physical world, right? So far, we have large language models, so they understand what humans have said about the world, but they don't necessarily understand how the world really works, because, right, what we say sometimes is ambiguous or even contradicting, and you know about hallucinations and confabulations and things like that. So as soon as those models better understand how the world really works, right, we can hopefully avoid that. And this is even bigger, right? There's even more understanding of the physical processes. How we don't want to learn everything. We know how physics work. How can we bring that together with these large language or large foundation models? So I think there's lots of opportunities to use quantum computers to bring them together. But that's an area where I expect a lot of work to happen. Thank you.
Okay, great. And the next question is from Daniel Marquez. And after thanking you for the talk, Philipp, do your use cases include the AI4 quantum approach you mentioned in the start? If not, could you give an example of that?
Absolutely. That's not an area. I mean, we are AI people, so we're focusing on using quantum computing for what we do on a daily basis. And I mean, we do a lot of transfer to industry, so that's what we focus on as DFKI. But for example, there is a group here at Saarland University. We're on campus, just a few hundred meters from here, by Professor Frank Wilhelm Mauch. They use these quantum hardware systems are very delicate systems. They're analog computers, right? You know about error rates and so on, and you need to run them in optimal conditions to get the best results. That's a physical process, and there's many knobs that you have to turn, so to say. Well, sometimes it's really knobs that need to be turned. To get the hardware into the optimal state, and keeping it there. And they use AI systems or AI approaches to automate that process of running the hardware in an optimal state. And there's multiple applications of AI for quantum computing in that general sense that I just described. But I think, I mean, that's absolutely that's really interesting. There's other applications as well. But I from my perspective at least, and I might be biased there, quantum computing, as you know, quantum computing doesn't give you necessarily exact results, right? It's more a probabilistic approach. You need to sample the result multiple times. And that is a really good match for a lot of the neural network stuff, because, as you might know, neural networks work with a stochastic gradient descent algorithm. So it, by definition, uses a stochastic input data. Actually, we often randomize the input to get better convergence on the neural network side. So this is actually a pretty good match here. And from my perspective, beyond quantum computing simulating quantum processes, which is a pretty obvious and direct application, I think the combination of quantum and AI might actually be the most effective use of quantum computing, because it seems like a really good match, and we can hopefully get a lot of feedback and a lot of impact from that.
Thank you, Philipp. And along the same line from Constanza Toninelli, she's asking, what about using AI to design experiments and problems that are optimal to show quantum advantage?
That's certainly an interesting application. not aware of work in that area right now, but I'm sure I would be surprised if no one is tackling that. That doesn't make absolute sense. I mean, the AI has to understand that space, right? And we have to learn, train the AI system in some way. So that is maybe not as easy as it might sound at first, but again, I'm not aware of research in this area right now. But certainly interesting.
All right.
Maybe can I add another question? Sorry, Oxana,
Please do.
Online. I was wondering if you can speculate about possible sort of European actions and policies that would help fostering this kind of joint innovation.
Yes, actually, the white paper that we wrote was on initiative by the Commission. So they asked us to write that. So I expect, or we expect that the Commission will focus some of the funding in this area, which is, I think, a really good thing because, right, as I said before, we're pretty good in both areas, and strengthening that combination is really good and important. I think, I mean, I'm coming from the AI side, right? So we are, and one of the things I'm advocating since actually 2017 at an OECD conference is that CERN for AI. That's what we brought up in 2017. We've been pushing for that. And funny enough, Ursula von der Leyen, after that was mostly seen as a crazy ideas of some professors, this now is a goal, is formulated as a goal for the Commission to achieve, designing and building that CERN for AI. And from my perspective, and by the way, there will be these gigafactories that are currently being, the Commission asked for feedback on that, and we're providing that. So hopefully we'll be able to design an infrastructure where also quantum computing will be integrated with AI algorithms. And there's a 20 billion euro investment into mostly the AI area for now, but as I said, hopefully there will be also the combination with quantum computing. For more policy, and if it's less on investment from the policy side, I think our main problem right now is that the classical infrastructure or the classical instruments to support research and then transfer to industry are classical projects, right? And if you think about that, so if there's a new area, we have to talk to the Commission, so they set up a call that easily takes a year. Then we have to write an application that gets evaluated. That often takes a year. And then we typically have 3 years time to work on that. And so I have to decide now, right, about the research I will do like 4 to 5 years down the road. And doing that in an area where kind of the key topics are changing on an almost monthly basis or quarterly basis, this is completely getting absurd, right? In terms of, so I think we need, and that's also the idea of a CERN for AI, so there will be funding that will be then in a more agile and dynamic way be allocated by the researchers who better understand where the problems are, and not go through that lengthy process. That's probably true for other areas of science as well. But in AI, it's just so obvious that we really need to move forward in this area. It's just, I mean, if you think about Google or other, how they do research, they have these what's called portfolio management approaches, where they combine the research and the development of multiple groups, right? You have clear connections between them, and they actually formulate a clear goal in whatever 1 year, 5 years. That is what we want to achieve, right? And in Europe, we're really good at doing incremental research all over the place, but we typically don't really have a clear goal that we want to jointly approach, right? The Quantum Flagship is one of those initiatives where that is more clear. and I really like that. But that program was canceled a couple of years ago. Unfortunately, from my perspective, I think from a policy point of view, in AI, it's absolutely clear we need to change the instruments that we're using in this area. But that's also not easy, as you might know. But it needs to be done. I mean, we're completely outdated along those lines.
Thank you.
You're welcome.
Yes, thank you very much, Philipp. There is one more question that I wanted to ask you regarding the annealing machine that you were using for one of your use cases. Would you share which exactly is the machine that you are using, and whether you are using some of the machines that are built in Europe?
We actually, I mean, as I mentioned, Franz Wilhelm Mauch, who's one of the key PIs of the quantum flagship, he's a professor here in Saarbrücken, and we have joint collaboration with Jülich. So yes, we are also using European quantum machines, and we want to do that more and more. Absolutely. I can't remember right off the top of my head with the examples that I gave which computers they were using. But I mean, our point is we don't necessarily want to use one specific computer. We want to develop algorithms, and some of the algorithms I talked about can run on a circuit-based machine. Others can work on an annealing machine, and we can actually have both cases. So we can have the algorithm run on either of them. So we're really looking more to make that quantum and AI a more software problem, right? Where we can hopefully abstract more and more from the concrete hardware. That's not always easy, and a lot of people are working on that. But we need to move in that direction, absolutely. I hope that answers your question.
Sure, yes. And if you would be able to state now the advancement in the quantum machines that are available of today that would allow you to do the next step to get the results of a next level, of the next quality, what would be that advancement that you would wish?
I mean, certainly error correction is probably the biggest. I mean, more qubits and less error, so to say, is really probably the most important steps, because then a lot of the algorithms that we're doing. So I mean, there is a cost to going between the classical to quantum and back. And so maybe having that to do less often, because we can do more work on the quantum side, would definitely be beneficial. The other, so that's one direction, and a lot of the algorithms that we designed would directly benefit for more capable quantum computers, or less error or more qubits. The other thing is what I already mentioned, is that software layer, right? Right now, you still have to tailor your algorithms to specific machines, building that. I mean, I'm always saying computer science really took off once we moved away from spaghetti code and go-tos and had a structural development process that really, where we didn't care about what the hardware looked like, right? And I would expect something similar to happen for quantum computing. We're doing good progress in that area, but there's still quite a bit of room to grow to make that even simpler and abstract that even more.
Thank you very much, Philipp. I think with this we are ready to close our session, and we appreciate a lot for you being with us, and looking forward for seeing our speakers at the next session. With this, I would like to close the recording.
Thank you very much, everyone.